Okay, here we have a one-dimensional motion problem with constant acceleration. This problem is not a free fall problem, so our constant acceleration will not be g. However, it is given. Let's read the problem. In this case, you're driving a car at 12 meters per second. That's our initial velocity. A deer jumps in front of your car. And we're asked what is the shortest distance for your car if your reaction time is 0.8 seconds and your car brakes at a rate of 6 meters per second squared. And when we say shortest distance, we mean shortest braking distance, so the wording there could be better. So we want to find the shortest braking distance. Okay. Okay, so that's what we're looking for. And the other thing that we want to consider in interpreting this problem is that we want to split the motion into two segments. Split motion of the car into two segments. And those two segments are before braking and after braking. Okay? Because we've got that reaction time. We've got 0.8 seconds where the car is going to be continuing to move at constant velocity at the 12 meters per second squared, and then we have the time where the car is decelerating. Okay? Has a negative acceleration. So let's draw a little picture here which shows our setup. Okay? So here is our car. Okay. Okay, we have some initial velocity. Okay, so this is our initial, that's our v naught. Okay, and everything's in the x direction. I'm going to define positive x as this way. Okay, then we're going to have some distance that's covered at constant velocity. So I'm going to call that x constant. Okay, so let's draw that here in the picture. Okay, so I'm going to say, okay, so for a while the car is going to continue to move, and it's going to move without decelerating. So x constant. Then the acceleration will start. Now notice I don't know these distances, but I do know the time, and then that's going to be the deceleration distance here. Okay, so we'll call this one, we'll call that x decel for deceleration. Okay, so those are the two distances, and then our deer over here is, right, there is our deer. Okay, so that's it. We want to, we want to stop before we hit the deer. Now, I mean, I guess I'm assuming we get right to the deer, but I just need to know, what's the minimum distance with this acceleration. Okay, so we want to then think all about motion. So the equations we want from our selection of kinematic equations are going to include motion and time, because we are given some times here. Okay, so first of all, let's find out how far we go at constant velocity. Okay, so x constant is just going to equal x naught plus v naught times t constant plus 1/2 a times t constant squared. Well, you might be thinking, well, hold on, there's no acceleration when the car is moving at constant velocity. So that whole third term goes to 0. And also, we can call our initial position, x naught, we'll just call it 0. That's just where we'll start our coordinate axis. That'll be our origin. So that means that the distance covered before braking begins is just going to be 0 plus 12 meters per second times 0.80 seconds, which will indeed give us a distance. Okay, so let's do 12 and multiply that by 0.8. Okay, so that's going to give us 9.6 meters. Okay, no rounding necessary there. So what I found then is that x constant is 9.6 meters. But now the reaction time's finally over, right? The person is now aware of the deer and knows that they want to stop. So now they're going to actually start stopping. And this is, you've probably heard this in car safety videos, but it is always quite interesting to think that, we continue to move, in this case, almost 30 feet before we actually start to respond to do anything. Okay, so now we want to find the rest of the distance, the deceleration distance. Okay, so decel, well, what's that going to look like? Well, that's going to be x naught, okay, and then plus v naught times some time that we don't know, and I'll get back to that, and then plus 1/2 a decel, so that's the actual rate of deceleration, times t squared. Okay? Okay, so what do we know here? Well, one thing is we think, well, what do we want to do with x naught? We could certainly set that to 9.6 meters, but it's not necessary in the way that I drew the picture. In fact, it would not be consistent with the way I drew the picture, because I didn't call x decel the sum of x constant plus the rest of the distance. I said it's just this additional distance. So then we can think of the total distance. So x total, which is what we're trying to solve for, that's going to be the shortest distance, is just going to be the sum of the distance we're moving at constant velocity plus the distance where we were actually decelerating. So my point is that we do want the initial position for the deceleration to be defined as 0. Okay, definitions and consistency are so important in these problems. And then we still have the same initial velocity, 12 meters per second, times some time we don't know, and then minus 1/2 times 6 meters per second squared, and then times some time we don't know. Okay, so this is, this is of limited use, right? Because we say, okay, well, we've got, we don't know the deceleration distance, and we don't know the time to cover that deceleration distance. So we have one equation, but two unknowns. That's not getting us anywhere, right? Even though we plugged in the information that we had, it didn't give us what we need, because we weren't asked for how long it takes for them to break, in which case maybe we would have been given the distance to do so. No, in this case, we need to find that distance. We need to find the deceleration distance. Okay, so we'll use a different kinematic equation. So I'll say, so since we don't know x deceleration or the time to do so, we will use different kinematic equation. Okay? And the kinematic equation we're going to use is going to be one that it relates velocity to distance. Okay? We will use equation of velocity as a function of displacement. Okay? So which one is that? Well, that's the kinematic equation that says v squared equals v naught squared plus 2a times x minus x naught. Okay. Well, x minus x naught is simply x deceleration, and we can see that right here because x naught is defined as 0, so x minus x naught, simply that total distance we're trying to solve. So let's clean this up with what we know. Okay, so we got v squared equals 12 meters per second squared minus 2 times 6 meters per second squared times the thing we're trying to solve for, x decel. Okay, so, and if you've been wondering about the minus, the reason that I know that the acceleration is a negative value is because it's opposing the velocity. So anytime your acceleration opposes a positive velocity, and here we called the velocity positive because I defined the positive x-axis as forward, a logical choice, it has to be a negative acceleration. And you can think about it formally like that, or you can just say, oh, well, braking is always going to be negative, right? So some sort of slowing down process creates negative acceleration. Okay, so you might say, oh, well, we're back to the same situation. We don't know v, and we don't know x deceleration, but we do know v. And v equals 0 since it is the final velocity after the car is stopped. Velocity after braking. All right, so it's just the car coming to rest, which was the whole goal anyway. All right, so now we can safely and confidently write 0 squared is just going to be 12 meters per second, quantity squared, minus 2 times 6.0 meters per second squared times the deceleration distance we're trying to solve for. Okay, so then when we actually solve for that distance, what is it going to look like? Okay, well, we're going to have negative 12 meters per second squared. Okay, and oh, I should put that negative on the outside. It's important, right? Because we squared it and then subtracted it. And then we're dividing by negative 2 times 6.0 meters per second squared. Okay, is this going to give us the correct units? Well, sure enough, because here we're squaring our meter, so we're going to have meters squared, and here we're not, it's just meters. So the seconds will all cancel, and we're only going to be left with units of meters. Okay, so let's go ahead and plug this into the calculator. Now, and I'll go ahead and I'll cancel the negatives, so we don't have to enter those in the calculator. So those cancel. So I have 12, okay, 12, and then I'm going to square that. And then we're going to divide by 12, 2 times 6. Okay, so it's just 12 squared divided by 12. I'm sure you can guess the answer. It's just 12, 144 times 12. Or, you know, we could just think about it exponentially, right? Because it's 12 to the power of 2 divided by 12 to the power of 1. Then we follow the laws of exponents. 2 minus 1 is just 1. So this gives us that the deceleration distance is just going to be, so x decel is just going to be 12 meters. Thus, our total distance, the thing we sought to find out, is 9.6 meters plus 12 meters, which is then going to be, all right, so let's add those together. 21.6 meters, our final answer. That's how long it takes them to brake, which is over 60 feet. So, you know, you can think, would that prevent you from hitting the deer? Often not. You have to swerve. Otherwise, you're going to get a deer rolling over your windshield. Okay? Thank you.